Okay, so some more problems using molarity here. So at the top of the page here, we've got another problem. How many milliliters of a 1.5 molar potassium hydroxide solution are needed to provide 0.0275 moles of KOH? So here again, 1 unit in terms of moles. This is a relationship between 2 units, moles of the solute and liters of the solvent. So this will be dimensional analysis type problem again. Start with the quantity of moles we want here, KOH. And in the second step, we want to put moles on the bottom. Remember, we're trying to cancel out moles here in our units. Since this is 1.50 moles of potassium hydroxide per liter of solution, I'm just going to invert it and put the 1.50 moles of KOH on the bottom, and that would put the 1 liter or liter of solution on top. Again, the 1 here is optional. Multiplying by 1 is not going to change your numbers, so you can put in the 1 if you like. You don't have to if you don't want to, but you do need the liter unit there. But here, this would cancel out moles, right, and get us to volume units, liters. Now what we want is a different volume unit, milliliters. So we would need one more step here where we cancel out liters. Excuse me. Cancel out liters, change our units to milliliters, and that will involve multiplying by 1,000 in this case. So 0.275 divided by 1.5 times 1,000. And we've got 3 significant figures to start with, so just 3 here in our answer. We would need 183 milliliters of that solution to provide that many moles of potassium hydroxide. Okay. This problem is a little trickier than the others because of the inversion, right? As we've seen before. So be on the lookout for that. If you're following your units, that shouldn't really give you too much trouble, but if you're not paying careful attention to your units, you can get something upside down here fairly easily. Okay, here's another example. We want to calculate the molarity of a solution made by dissolving 0.750 grams of sodium sulfate in enough water to form exactly 850 milliliters of solution. So here again, calculating molarity, we just need to know our definition. Molarity is going to be moles of solute over liters of solvent. We don't actually have either of those right here, but we should be familiar enough with how to get there. So let me start with our solute. We've got 0.750 grams of sodium sulfate. Now to get to moles, of course, we need to use the periodic table, find the masses of the atoms in that molecule, and then add those together. So let me do that down here. We've got 1 sodium. Well, we've got sodium. There's actually 2 of them. So we'll multiply 2 by the mass of sodium, which is 22.99. 1 sulfur. So sulfur is 32.07. Right? And 4 oxygens in the sulfate. So that would be 4 times 16.00. Now, combine all that together, and I'm going to combine it all in the calculator. Don't forget that we're multiplying by some of those. So that, I added all those up, and it came out to 142.05. So that would mean that 1 mole of sodium sulfate weighs 142.05 grams. And that would give me moles of my solute, the sodium sulfate. So 0.75 divided by 142.05 is 5. Okay, so remember we're limited to 3 sig figs. I'm going to keep a couple extras here, although I don't want to have to write out everything on my calculator. So I'm going to keep it in the calculator. I'm just not going to write everything out. 5.2 8 basically times 10 to the minus third moles of sodium sulfate. Now the other piece of information we said we needed back here for molarity is liters of solution. That's also going to require a conversion. If we have 850 milliliters of solution and 1 liter is 1,000 milliliters, that will be 0.850 liters. Now that we're talking about liquids, this is a conversion we're going to do all the time. So you may get to the point where you're comfortable enough just saying, yep, milliliters to liters, I'm going to move my decimal 3 places, and vice versa if we're going from liters to milliliters in the other direction. That's perfectly all right. However, right, if you have any hesitation at all, line up your units, and then you'll always move in the right direction. Okay, the molarity here then will be the quantity of moles divided by the volume. So our 5.2798, although that's sitting now in my calculator, divided by 0.850. So previous answer divided by 0.85. And now I do want to round to 3 sig figs because, actually no, I want to go to 2 sig figs because this 850 did not have a trailing decimal, so this 0 actually should not be there. When we turn that into liters, that's really a 2 significant figure volume there in terms of liters, so our answer should just be 2 significant figures. 6.2 times 10 to the minus third would be the molarity of this solution. Okay, yeah, gotta watch the sig fig, so I almost caught myself there. All right, last question here. You have a stock solution of 14.8 molar ammonia. Now, a stock solution is basically something you might keep in a laboratory. It would be a fairly highly concentrated solution of a particular chemical that you may use a lot of, and you would use that solution to create usually more dilute solutions that are convenient for a particular experiment. So you might keep concentrated acids that you can store in a relatively small amount of space, but then dilute them for experiments where you don't need the solutions to be so concentrated. So in this case, our stock solution of ammonia is 14.8 molar. What we want, though, is to make a full liter, so 1,000.0 milliliters, of 0.250 molar NH3. So what we want to do in this case is what's called a dilution. So this is an important thing to watch out for. And the important thing to recognize about a dilution is what's changing is the amount of solvent. But what's not changing is the quantity of solute that is present. So moles of solute doesn't change. So we take our concentrated solution, we dilute it to this concentration, we have the same number of moles of solute. Well, moles we could think about calculating moles if we take molarity, which is moles per liter, and multiplying by liters, right? Because liters would cancel out, that would give us how many moles. So this leads us to a very useful equation that you can use when you're doing a dilution. And I like to use C's and D's here. The molarity of the concentrated solution times the volume of the concentrated solution will be equal to the molarity of the diluted solution times the volume of the diluted solution. Now, if we're doing a dilution, we should have 3 of those pieces of information, right? Which we do here. We've got the original concentration, we've got the target concentration for the diluted solution, and how much of the diluted solution we want. We just need to rearrange this equation and solve for what's missing, the one missing variable. Now, in a lot of textbooks, this is M1V1 equals M2V2. I find people sometimes get confused as which one's 1, which one's 2. Concentrated dilute maybe makes that a little easier to make sure your pieces are going in the right place. Because when I rearrange this, right, what I want to know is what's the value I need of that concentrated solution. So I'm going to divide through by the molarity of the concentrated solution. Right, so that I isolate what I'm trying to solve for on the left here. And now I just need to plug in the other pieces. And this little dot, it looks a little bit like a minus there, depending on how I write it. It's a multiply, so don't mistake that for a subtraction. So molarity of the dilute solution we want is 0.250 molar. The volume we want is 1,000 milliliters. Right? And if I leave this volume in milliliters, that means my answer will be in milliliters. So that's convenient. It doesn't necessarily have to cancel out here because it'll cancel out. The other units will cancel out when we stack one molarity over the other molarity. 14.8 molar is my concentrated molarity. Right? And here's where dilute and concentrated help, because if you flip those around, they're both molarities. If you don't know which one is 1, which one is 2, you can maybe get this upside down. Molarity is going to cancel out here. We'll be left just with milliliters, right? And this again will be the volume of the concentrated solution that we're looking for. So 0.25 times 1,000 divided by 14.8 is, and it looks like 3 significant figures is our limit. We would need 16.9 milliliters of that concentrated ammonia stock solution, right? And then when we dilute that to the 1,000 milliliters, that would give us a solution with the concentration we're looking for. So watch for that. If you see the term dilute in a problem, or even if you just see the description of adding water to make a solution more concentrated, you're going to want to think about this equation and how it relates to that problem. Okay. Stop there on that video, and we'll pick up on the next page in the next one.